Welcome to Lecture 13 of How to Read and Do Proofs. Welcome back, everybody. Today we're going to learn the either-or methods, which surprisingly you should use when you see the keywords either-or in either the forward process or the backward process. Let's take a look at an example. If x squared minus 5x plus 6 is greater than or equal to 0, then either x is less than or equal to 2 or x is greater than or equal to 3. These keywords can be hidden. For example, if a and b are integers for which a divides b and b divides a, then a equals plus minus b. Where are the keywords either or here?
In the plus or minus b, a could equal positive b or negative b.
Exactly. That is, either a equals plus b or a equals negative b. So watch out for these hidden keywords. Okay, as I mentioned, these keywords can appear in either the forward process or the backward process. So as usual, we have two different proof techniques. Let's talk about the either-or methods in the forward process. This is actually called a proof by cases. And so the setting is something like this. You want to prove that if either C is true or D is true, then B is true. With the forward-backward method, you can assume that either C is true or D is true, and your job is to show that B is true. So if you think about working forward from either C or D being true, you should have a question. What question?
Which one to work forward from?
Right. Is it C that's true or is it D that's true? So for example, if it's C that's true, then you should work forward from C to get to B. In contrast, if it's D that's true, then you should work forward from D to get to B. Right? Okay. So we don't know which of these two statements, C or D, is true. We know one of them is true at least, but we don't know which one. So we don't know whether to work forward from C to get to B or whether we should work forward from D to get to B. So here's what we're going to do. We're going to protect ourselves by doing two proofs. The first proof is to assume that C is true and show that B is true. The second proof, which we'll call case 2, is to assume that D is true and show that B is true. Do you agree that if we do both of these proofs, then it doesn't matter whether it's C that's true or whether it's D that's true? Because if it's C that's true, you can use the proof in case 1, and if it's D that's true, you can use the proof in case 2. Let's take an example and see how this actually works in practice. Here's a definition of a maximizer of a function. A real number y is a maximizer of a function if and only if the value of the function at y is as big as possible, meaning you get the largest possible value for the function when you put in the value y. With quantifiers, it reads this way. A real number y is a maximizer of a function f if and only if, for all real numbers x, the value of the function at y is bigger than or equal to the value of the function at x. And now what we'd like to prove is that if a, b, and c are real numbers with a being strictly negative, then y equals minus b divided by 2a is in fact a maximizer of this parabola. By now you have learned to identify the hypothesis A and the conclusion B. You know that the next step is to choose a proof technique based on keywords that you see in the proposition. What proof technique would you use to start this proof and why?
The forward method, since there's no keywords.
The forward-backward method, because there are no keywords. Correct. So let's do that, and let's ask the usual key question. How can I show that
A number is a maximizer of a function?
Exactly. How can I show that a number is a maximizer of a function, for which we will, as usual, use a definition to provide the answer? So according to the definition, we have to show that for all real numbers x, ay squared plus by plus c is greater than or equal to ax squared plus bx plus c. Now look at b1. Can somebody tell me what proof technique we should use now?
The choose method.
Why?
Because of the quantifier for all.
When you see the keywords for all in the backward process, you have to show that for every object with a certain property, something happens. So you should think about the choose method. And therefore you would choose what in this case?
A real number x?
A real number x, for which you have to show that
ay squared plus by plus c is greater than or equal to ax squared plus bx plus c?
Exactly. Now we have to fill in the details here of the model proof by doing the forward-backward method. So let's go ahead and do that. Let's work backward here by cleaning this up a little bit. Let's cancel the c from both sides, bring the ax squared plus bx over to the left side, and then factor out y minus x. And if you do that algebra, here's what you have to show. You have to show that y minus x times this quantity is non-negative. Okay, now let's look at the quantity y minus x. Do you agree that if y minus x is equal to 0, then the statement B3 is true? Okay. For doing this proof, you might as well assume that y minus x is not 0, because if it is 0, you would be finished, correct? So let's think about what happens if y minus x is not 0. Well, if y minus x is not 0, what is it?
Greater than 0?
Or less than 0?
Perfect. Either y minus x is greater than 0 or y minus x is less than 0. And now I hope you see in the forward process the keywords either or. Either y minus x is positive or y minus x is negative. And this is when you want to start thinking about using the either or methods. Because we see those keywords in the forward process, think about using a proof by cases. So in this example, y minus x greater than 0 is, let's call it the statement C, and y minus x less than 0 is the statement D. So you want to show that if C or D is true, then B3 is true. And this is where we're going to use a proof by cases. So now you have to remember how a proof by cases works. In particular, we have to do two proofs. Let's talk about case 1. What should I assume is true in case 1?
That C is true?
That C is true. And what do you have to show?
That B is true?
That B, in this case, B3 is true, exactly. And just to be sure that we understand this, here you see case 1. Let's do case 2. What should you assume is true when you do case 2?
That D is true?
That D is true, for which you have to show that
B3 is true?
B3 is true. There are the two cases. So it's exactly what I'm going to do. I'm going to do case 1 first, and then I'm going to do case 2 afterwards. Now the rest of this proof involves nothing but a lot of algebra to go from A4 to B3, and then again from this A4 to this B3. So I'm going to go through the algebra a little bit quickly because that's not the focus of the lecture, but I'll show you that algebra right now. So let's try to show from case 1 that if y minus x is positive, then B3 is true. Now if we know that y minus x is positive, let's work backward by algebra from here by dividing both sides of this inequality by y minus x. And because that's positive, this inequality doesn't change. So let's work backward and say to show that B3 is true, let's just cancel the y minus x. So we have to show that a times y plus x plus b is non-negative. Okay, so here's some more algebra. We're going to work forward from the hypothesis that y is equal to minus b over 2a, and a is less than 0. Both of these are given in the hypothesis. And we're again going to use A4, which says that y minus x is positive. So in particular, if you replace y here with minus b over 2a, then you can say from A4 that minus b over 2a minus x is positive. And now if you take this inequality and multiply both sides by minus 2a, which is positive. Why is minus 2a positive? A is negative, and minus 2a is therefore positive. So if you multiply this inequality here, both sides of this inequality, by minus 2a, which is positive, you get 2ax plus b is strictly positive. And now let's start with the left side of B4 and show that it's non-negative. So here's the left side of B4, a times the quantity y plus x plus b, and let's apply some algebra. In particular, y is equal to minus b over 2a. So let's just put that in for y. And now let's do a little bit of cleanup. And finally, let's put this over one common denominator of 2. So 2ax plus b divided by 2. But 2ax plus b from A5 is strictly positive, so this divided by 2 is strictly positive. And that's what we had to show in B4. So that completes this case 1. Now let's do that case 2. In case 2, if you look back on the previous slide, we can assume that y minus x is negative, and we have to again show that B3 is true. So now we're just going to work forward from A4 to get to B3, again by algebra. And the algebra is very similar to what we did right here. So let's just repeat the steps. In this case, y minus x is negative. So what happens when you divide both sides of B3 by y minus x?
The inequality sign changes.
Right. This inequality sign right here becomes a less than or equal to. So here's our new statement B4. And now we're going to do exactly the same thing we did in the previous case. We're going to work forward from the hypothesis that y is equal to minus b over 2a and a is negative, and from A4, which in this case is y minus x is negative. So here's some algebra. Let's replace y by minus b over 2a, and that has to be negative. And again, multiply through by minus 2a, which is still positive because a is negative, so minus 2a is positive. And you get 2ax plus b is negative. And now, as a forward step, I'm going to start with the left-hand side of B4 and make it less than or equal to 0. So here's the left-hand side of B4. For y, let's put in minus b over 2a. And now let's just clean this up. And as before, let's put this over the common denominator of 2. So 2ax plus b, the whole thing divided by 2. But 2ax plus b is negative from A5, so when you divide it by 2, it's still negative. And that's exactly what I had to show up here in B4. If you look at this proof by cases, you'll notice that the proof of case 2 is very similar to the proof of case 1. The only difference is some of the signs of the inequalities. Some of the inequalities have reversed directions. So we had greater than gets changed to a less than. When the proofs for case 1 and case 2 are very similar to each other, no mathematician in their right mind would write out the two cases. This takes far too much work. So what they would do in a condensed proof is they would do one of these cases and leave the other one for you to do. And the way you'll recognize that they are doing a proof by cases and doing only one of those cases, when you see the words assume without loss of generality that case 1 happens. So what this means is they're going to assume case 1 happens, do the proof of case 1, and then simply leave it for you to repeat or modify the proof for case 2. Let's turn to the keywords either or appearing in the backward process. When you see the keywords either or in the backward process, this is going to be called a proof by elimination. So here's the setting for this kind of a proof. You want to show that if A is true, then either C or D is true. So let's think about, again, using the forward-backward method. If you look at this statement, if A is true, then either C or D is true. You can assume A is true. Your job is to show that either C is true or D is true. So suppose you start working forward from A, and you get to A1, and you get to A2. As you proceed forward, where are you trying to get to?
Either C or D.
Either C or D, and so you should now have a question as you are working forward. What question do you have?
Which one should I get to?
Which one should I get to? Exactly. And so what we're going to do to help you is eliminate that uncertainty. And that's why we call it a proof by elimination. With the forward-backward method, you would assume A and show that either C is true or D is true. As you work forward from A, the question is it C that you should try to show is true, or is it D that you should try to show is true? To eliminate that uncertainty, let's think about the truth of C. C could be either true or false, correct? If C happens to be true, then the statement C or D is automatically true. And therefore, you would have nothing to prove. You would be done. So we only need to think about what happens if C is not true. If C is not true, what had better happen?
D would need to be true?
It had better be the case that D is true, and in fact, that's what you're going to need to show. Let me summarize a proof of elimination for showing that A implies either C or D. With a proof by elimination, you should assume that A is true and C is not true. As we said, in this case, it had better be that D is true. And so, in fact, it is your job to show that D is true. And now you're going to use the forward-backward method. Work forward from A and not C, and backward from D. Any questions on how this is working?
Could you also work forward from A and D, or A and not D, and then work backward from C?
Excellent. That's coming later in the slide, but that's perfect. The question is, can you work forward from A and not D, and then show that C is true? The answer is absolutely. Either one of those two proofs is acceptable. And we'll see that now again. Okay, let's see it in an example. This one is very easy. If x squared minus 5x plus 6 is greater than or equal to 0, then either x is less than or equal to 2 or x is greater than or equal to 3. And in this case, here you see the key words either or in the backward process. And this is what should trigger you to think about a proof by elimination. Here's the hypothesis A, here's the statement C, and here's the statement D. Let's use a proof by elimination. So what should we assume is true?
A and not C?
A, which is x squared minus 5x plus 6 is non-negative. And what's not C?
X is greater than 2.
X is greater than 2. And where do we have to get to? What do we have to prove?
X is greater than or equal to 3?
That D is true, which is x greater than or equal to 3. Exactly. And here, this is a very simple process of working forward by algebra to get from A and A1 to B1. Let's do the algebra. From A, let's factor. From A1, we know that x is greater than 2, so what about x minus 2?
It's positive.
It's positive, so again, we can divide both sides here by the positive number x minus 2. We're left with x minus 3 is greater than or equal to 0. And now, to get from A3 to B1, all we have to do is add 3 to both sides. Getting back to your observation, Hannah, it is completely true that you could equally well have done this proof by assuming A is true and D is not true, and then showing that C is true. Let's take a look at how that would work in this example. Same proposition that we had before, with the same statements A, C, and D. Recognizing the keywords either or in the backward process, we're going to use a proof by elimination. Only this time we're going to assume that A is true and D is not true. In other words, what are we going to assume?
X is less than 3?
That x is less than 3. And we have to show now that what is true?
X is less than or equal to 2.
X is less than or equal to 2. And again, it's nothing more than simple algebra to work forward from A and A1 to get to B1. Let's do the algebra. From A, you can factor. Again, this time x is less than 3, so x minus 3 is negative. When you divide by both sides, that inequality is going to reverse. And now if you simply add 2 to both sides of A3, you get B1. And that completes the proof.
Is there a specific time when you should use not D or not C?
It's a great question. Is there a specific time when you should assume A and not C and try to prove D? Or is there a time when you should assume A and not D and try to get to C? One time I would consider assuming A and not C is when C already contains the keyword no or not. Because then when you take the not of that statement, the no goes away and you get something useful. If you don't see the keyword no or not explicitly, then it's sort of trial and error. Try one, see if it works. If it doesn't work, try the other one, see if that works. Make sense? Yeah. All right, let's do an in-class exercise for practice here. Let's see if you're comfortable with these two proof techniques, proof by cases and proof by elimination. Suppose you want to prove that if either C is true or D is true or E is true, then B is true. Let's see how we would do that. First of all, are we thinking about a proof by cases or a proof by elimination?
Proof by cases.
Proof by cases because the either or is in the forward process. So that means we have to do several proofs. How many in this case?
3.
What 3 would we have to show?
Assume C is true.
And show that
B is true.
There's case 1.
Assume D is true and show that B is true. And assume that E is true and show that B is true.
Perfect. You have to do all 3 of these. In contrast, how would you prove that if A is true, then either C or D or E is true? First of all, is this going to be a proof by cases or a proof by elimination?
Elimination.
Proof by elimination because the keywords either or appear in the backward process. How would this work? What should you assume and what should you try to conclude?
Assume that A is true and not C is true, and not D as well?
That's correct. Assume A is true, C is not true, and D is not true, and then what would you have to show is true?
E is true.
Correct. Alternatively, you could assume A is true, C is not true, and E is not true, and show that D is true. Or you could assume that A is true, D is not true, E is not true, and show that C is true. Doing any one of these is all you need. Let's do another in-class exercise. How would you prove that if C or D is true, then E or F is true? First of all, are we going to do a proof by cases or a proof by elimination?
Can you use both?
You're going to end up using both. So let's start with the proof for the either or in the forward process. Which proof technique is that?
Proof by cases?
Okay, so proof by cases. So what's case one? You should assume what and show what?
Assume that C is true.
And show that?
E or F is true.
That's case one. Assume that C is true and show that either E or F is true. What is case two?
Assume that D is true.
And show that?
E or F is true.
Exactly. Now let's go to case one. How do we do this? What proof technique will we use to show that if C is true, then either E or F is true?
Elimination.
Elimination. So how does that work? We assume that C is true and E is not true. We have to show that
F is true.
F is true.
Or you can assume that
C is true and not F is true, and show that E is true.
Perfect. Let's go down here to case two. When you're finished with case one, then you have to come down here and do case two. To show that if D is true, then either E or F is true, just like up here, it's a proof by elimination. So we can assume D is true and E is not true. We have to show that F is true. Or we can assume that D is true and F is not true and show that E is true. Either one of these two will work. Okay, let's summarize the two techniques that we've learned today. First, proof by cases. You should think about using this method when you see the keywords either or in the forward process. For example, if you want to prove that if either C is true or D is true, then B is true. To use a proof by cases, you have to do two separate proofs. First, assume that C is true and then show that B is true. Then assume that D is true and show that B is true. With a proof by elimination, you want to think about using this technique when you see the keywords either or in the backward process. So for example, if you want to show that if A is true, then either C or D is true, think about a proof by elimination in which you assume that A is true and C is not true, and then show that D is true. Or if you prefer, assume that A is true and D is not true, and show that C is true. That completes this lecture.